So to start, the properties of the region of convergence with some examples. Have you done the question whatever we have given in the previous lecture? Okay. If you have done the question, then you will clearly understand the region of convergence, how the pole and zero, the location of pole and zero, it depends on the region of convergence, or the existence of position of pole and the zero can be determined in the region of convergence whether it located. So suppose before we start the region of convergence, a little elementary knowledge of pole and zero should be required. So suppose a rational function Laplace transform can be written in the form of a rational function like Laplace transform of any function x of t can be expressed in the form of x of s, as the x of s is equal to polynomial of numerator divided by polynomial of denominator. Means example, you can say a naught s to the power m plus a1 s to the power m minus 1 plus a2 s to the power m minus 2 and so on up to am is polynomial in s. Another denominator polynomial b0 s to the power n plus b1 s to the power n minus 1. Please mute anyone. I have not muted. There is a background noise. Please mute everyone. Please mute. Ashutosh, mute करो. So this expression as a rational function, you can see here numerator polynomial in s and denominator polynomial can be written as polynomial function of m divided by denominator function of ds. This can also be similarly similar function can be also expressed as a factor of some components. Suppose the term is some constant a s minus z1, where z is a constant value, s minus z1 into s minus z2 into s minus zm divided by s minus p1 into s minus p2 and so on up to s minus pm. If the value of m is greater than, sorry, here it should be n. If m is greater than n, then it is not a proper or improper kind of improper rational function. If n is greater than, it is improper or not proper, we can say. proper rational function if n is greater than m, then this rational function, then function f of x of s is proper rational function. Here all the roots of this function this function this function is called numerator polynomial, numerator polynomial, and this function is called denominator polynomial. So we can define here two terms. One, the root of this numerator polynomial, and another is the denominator polynomial, root of this denominator polynomial. So the root of the roots of or the solution of this roots of numerator polynomial is called 0. Zeros, if more than one, it is called zeros. Why it is called zeros? Because this root will lead the polynomial function is equal to 0. If you find the value of s, means root of this polynomial, numerator polynomial, for that value of root, you will get x of s is equal to 0. That's why it is called zeros of x of s. Another terms are the pole or the roots of denominator polynomial is called pole. If more than one pole, then it is called poles. Poles of x of s. Pole means this root will lead x of s is equal to infinite. Means x of s will not, that is x of s will not converge, will not converge for this roots of denominator polynomial. This is the difference. This is the definition. You can say denominator polynomial. So you will see whenever you plot the region of convergence, there may be the chance that 0 may lie inside the region of convergence or outside the region of convergence, but in the region of convergence there is not possibility of the existence of poles. Means we can conclude, note, the pole cannot lie in the region of convergence, because region of convergence are those
सर वॉइस
regions.
स्लो आ रही है सर आपकी।
Yes.
सर थोड़ी
हेलो,
स्लो आ रही है सर।
क्या दिक्कत है?
वॉइस स्लो आ रही है सर थोड़ी आपकी।
वॉइस स्लो आ रही है।
सर नहीं आ रही है।
अब ठीक है? हाँ,
यस सर।
the pole, by the definition here, definition of this pole, this is denominator polynomial, root of the denominator polynomial, that is where the value of this x of s will become infinity. Root where x of s will become infinity, that is it will not converge. Infinite means undefined value, defined value, undefined value. So at that particular value of pole x of s will not be converged. So we can say pole will not lie in the region of convergence, because region of convergence is the region where x of s x may exist or always be some convergible value, some existence will be there for the Laplace transform of x of s for the function. But pole is the point where this x of s will not converge. So we can say pole cannot lie in the region of convergence. This is very much important property of region of convergence. Suppose function x of s is equal to 2s plus 4 divided by s square plus 4s plus 3. For region of convergence, ROC is real part of s greater than minus 1. For this region of convergence, a Laplace transform is defined like this. Now, the location of pole and 0 can be plotted by this expression. This expression can be factorized as take the common 2, it will become s plus 2 into 2, and this denominator polynomial can also be factorized like s plus 1 into s plus 3 for this region. Now you can plot here, see this is denominator polynomial, this is n of s is equal to s plus 2, and here denominator polynomial d of s is equal to s plus 1 into s plus 3. So here n of s, solution of n of s will roots of n of s is equal to minus 2, and roots of d of s will be s is equal to minus 1 and s is equal to minus 3. Put this value is equal to 1, try to simplify this simple polynomial, solve like this, you will get this value. This is called zeros and this is pole. Now pole and 0 can be plotted or visualized in the graph using simple notation as either cross or
सर
yes.
सर इसमें रूट के जो जीरो रूट एन एस होगा तो उसके जीरो उसको जीरो बोलेंगे और जो डी एस होगा उसको पोल बोलेंगे।
हम्म।
ये यस सर,
हाँ हाँ ये
यही डिफरेंस है ना सर?
हाँ हाँ।
ओके सर।
और पोल को नोटेशन, पोल का नोटेशन क्रॉस, तो छोटा क्रॉस से किया जाता है, और जीरो को नोटेशन, जीरो को इसको डिनोट करने के लिए एक छोटा सर्कल या जीरो बोल सकते हैं, इस तरह से ओ, ये नोटेशन है, कन्वेंशन हमेशा ये यूज होता है हर जगह। सो यहाँ देख सकते हो एस इज इक्वल टू माइनस 1 एंड एस इक्वल टू माइनस 3 आर द पोल्स। सपोज इन दिस complex plane, S plane, vertical axis is imaginary axis, horizontal axis is real axis. This is 0 anywhere in this side 1, this is 2, this is 3, in this side here minus 1, here minus 2, here minus 3. So S is equal to minus 1 and minus 3, मतलब यहाँ पे सिग्मा 0 है, S इज इक्वल टू माइनस 1 होने का मतलब है सिग्मा प्लस जे ओमेगा इज इक्वल टू माइनस 1, है ना। तो इन दिस हियर यू कैन सी नो इमेजिनरी टर्म इज प्रेजेंट, तो इसका मतलब सिग्मा इज इक्वल टू माइनस 1 है और ओमेगा इज इक्वल टू 0 है। क्लियर है ना। ओमेगा इज इक्वल टू 0। ओमेगा 0 और सिग्मा इज इक्वल टू -1, मतलब कहीं भी यहाँ पे एक पोल लाई कर रहा है। क्रॉस से दिखाते हैं वन लोकेशन ऑफ पोल, another location of pole is -3, it means this here. There is a chance that solution of this for the pole s is equal to -1 plus j5, या इस तरह से भी हो सकता है, कॉम्प्लेक्स वैल्यू, ये s का वैल्यू कॉम्प्लेक्स भी हो सकता है। तो उस टाइम में कहीं इस रीजन में लाइक रहेगा, मतलब इमेजिनरी पार्ट और रियल पार्ट दोनों वैल्यू नॉन जीरो है। इस केस में हम लोग जो देख रहे हैं यहाँ पे इमेजिनरी पार्ट जीरो है, दैट्स व्हाई लोकेशन ऑफ पोल इज ऑन द रियल एक्सिस। ठीक है, ये चीज़ क्लियर रखना। कोई दूसरे एग्जांपल में कभी देखोगे तो ऐसा नहीं है कि इसमें प्लॉट करना है। फिर अनदर, here you can see s is equal to -2, this is 0, so 0 can be notation like this. So in this complex plane, pole and 0 is located like this. Now the region of convergence is what? S greater than real s greater than -1, means starting from this -1 greater than this region, all the value from -1 to infinite. This is the region of convergence. So here you can see the region of convergence uh, will not contain any pole. Now coming to the other properties of region of convergence, that if suppose uh, f of t is like finite duration signal, you can take an example like u of t minus u of t minus 5, this function is given, then their region of convergence will be all S plane, entire S plane except S is equal to 0 and S is equal to infinity. These two values will be accepted or eliminated from the region of convergence. All the possible values can be accepted. You can consider this example any finite duration signal. For any finite duration signal, this is the one example of finite duration signal. ROC will be like this. This is one property. You can solve this example and try to see any time duration signal or whatever you find. You can consider that example by your own intuition. See, x of t is equal to ut minus 5. So the plot, if you see function f of t, it will like this. Is this finite duration? Yes, it is finite duration signal. So now try to find the Laplace transform as well as region of convergence. So to find Laplace transform of f of t, we integrate from minus infinity to plus infinity f of t e to the power minus st dt, and uh, we are not interested to find, sorry, Laplace transform. We only see the region of convergence, because Laplace transform is simple, you can find, you solve this. But region of convergence, you have to check the integration from minus infinity to plus infinity f of t e to the power minus sigma t. Integration of this should be finite. See what are the possible value of sigma for this. This integration will converge. Here f of t is from 0 to 5. It's integration from 0 to 5. The value is 1 and e to the power minus sigma t dt. Now check the value of sigma for which this integration will be convertible. Yes, all the value of sigma, all the value of sigma is acceptable or possible to converge the Laplace transform. When you take another example, you will see another uh, the value. Uh, See, if you consider sigma is equal to plus infinity, then it is okay. Then if you consider sigma is equal to minus infinity, that possible that value should be not considered, except sigma is equal to minus infinity. So in some example, you will see that sigma positive value or sigma negative value of infinity or some sigma is equal to 0. All these value will be left or eliminated from the region of convergence. All possible value will be considered. So this is one property of region of convergence. Please keep in mind for any finite duration signal, the ROC will be entire explained except the possible value of these 2 points. Another property of region of convergence is when signal is right-handed signal. When x of t is right-sided or right-handed signal, then right-sided means a causal type of signal like this. X of t is exponentially decreasing for this type of signal. You can say here this is right-sided. Then ROC will be then ROC. See any example if you have done in the previous discussion or the examples. In this type of signal, ROC was real s greater than any particular value sigma. That sigma is maximum value or the rightmost possible value of pole. Rightmost sigma max is rightmost or the maximum value of pole. Better to write maximum possible value of a real part of pole. This is a simple example. If you consider f of x of t is equal to e to the power minus 5t ut. Another example, if you consider uh, something plus e to the power minus 2t u of t. In this case, you will see there is 2 of pole s is equal to either minus 5 or s is equal to minus 2. So your in this case ROC will be real s greater than 5. Like this you can find a simple uh, way or shortcut method you can also apply. To find the region of convergence, shortcut ROC will be real part of S greater than is equal to uh, pole, or the maximum value of all poles. Maximum of all poles. If you find more than one pole, then the region of convergence will be right side of the maximum value of the pole, maximum or largest location of the pole. Another property is when x of t is left-handed signal. For simple this example of causal signal. और लेफ्ट हैंडेड मतलब नॉन causal signal, anti causal signal. When x of t is left sided signal, then ROC will be the real part of S less than the sigma. See the example when you take x of t is equal to e to the power minus 5t or u of minus t, like this type of signal, left sided. In this case, ROC will be always like this. So pole is this 5, location of pole is here. This is imaginary part. This is the real part sigma. So this will be the region of convergence. So anywhere you see the region of convergence is uh, somewhat left side from a fixed line. Anywhere, suppose region of convergence is like this, from this straight line, left side of this line. So you can say this region of convergence will be for left-handed signal, left-sided signal. Anywhere if you see region of convergence is like this, you can say this is right-sided signal. So this type of property you should clear. Next property is when two-sided signal. When x of t is two-sided, either both sides, either in the left side or right side, both two side is considered two-sided signal. Then ROC will be a real part of S less than sigma max and greater than this is the region between two pole, the region between two pole or existence of region of convergence. Like this example, you can see x of t is two-sided, means both sides, either left side, consider e to the power minus 5t ut. Here you consider e to the power 5t u of minus t. This is two-sided signal. Here you will see ROC is between minus 5 to plus 5 in this region. Actually, it will looking like this. One region of convergence is greater than minus 5, another will be left side from the 5. Now the common of these two will be only this is common. Up to my minus 5, the real part of s greater than this is the common range. So here if you see both two-sided signal, the region of convergence will be a parallel strip of vertical axis like this type of. So these are the some behavior of region of convergence for different type of signal. You will observe if you do multiple number of examples related to some different type of signals. Now coming to some properties of Laplace transform. Some properties of Laplace transform is also important. You should know that to one example, if f of if Laplace transform of Laplace transform of x of t is given as x of s, then Laplace transform of x of t minus t naught, Laplace transform of x of t minus t naught. To do, you follow the simple steps whatever we have discussed about this Laplace transform. That is what Laplace transform of any function is defined as integration from minus infinity to plus infinity x of t minus t naught e to the power minus st dt. And so here if you put t minus t naught is equal to u, so dt will become du, and so this Laplace transform will become from minus infinity to plus infinity, because the range is minus infinity, so this substitution will not change anything. So here x of u e to the power minus s, here t is equal to u plus t naught du. And so by simplifying this expression, x of u e to the power minus s u into e to the power minus s t naught into du. Further simplified, here this expression is constant with respect to u, so keep outside from the integration, it will become e to the power minus s t naught integration from minus infinity to plus infinity x of u e to the power minus su du. Here you can see this expression is nothing but the difference is that only the integration parameter same, it is x of s. So the modified expression will be e to the power minus st naught into x of s. So here we conclude that if x of t having Laplace transform f of x of s, then x of t minus t naught will be in the frequency domain as e to the power minus t naught into x of s. So if you shift in shift in time domain, signal will change here. Multiplication in with multiplication by phasor in s domain. This is called time shift property. Time shift property of Laplace transform. This is called time shift property of Laplace transform. And what about the ROC? Since this is the phasor and x of t is same as the previous x of s, so if region of convergence of this x of s is here uh, R, the same R, region of convergence of this will also be same. So this is one property, that is you shift in time domain, it will lead the multiplication with phasor in s domain. Now if you uh, scale in time domain, x of at, what will be the Laplace transform of this signal? Proceeding with the same approach, Laplace transform, integration of this x of at e to the power minus st dt. Here also substitute at is equal to u, and so dt is equal to 1 by a du. It will become integration from minus infinity to plus infinity, x of u e to the power minus s u by a, and dt is equal to 1 by a du. Correct? Is it correct? X of at, x of u e to the power minus s at this. So this is constant 1 by a, keep outside, integration from minus infinity to plus infinity, x of u e to the power minus s by a into u to u du. Here this expression is similar to the formula that we use to transform Laplace domain, but with the difference that here s is given as s by a. So wherever s is present, you put 1 by s. X of s, you will take now x of s by a. So this is Laplace transform of x of at will become 1 by a x of s by a. And what about ROC? Here ROC will be different because time is scaled. So if ROC is here, ROC of x of t, x of s is R, ROC of x of s is r. Then if you substitute here s with s by a, substitute s with s by a. So here in the same factor, ROC will be ROC of x of s by a will become a into. Like this, you can do all the different type of question in the similar way. In giving some question, please try to find one question is try to find the Laplace transform of this signal if you know the Laplace transform of x of t is x of s. Another, find t into xt. This is called time multiplication, frequency, time differentiation. If you know these two properties, then you can use some another also. Try to simplify e to the power minus 80 ut. Try to simplify t into e to the power minus 80 ut. Laplace transform. If you know the basic signal transformation from time to s domain, then you can use property of this Laplace transform also to find another different type of examples. Either of the method, either you go through the conventional approach, like different question you have to solve a lengthy integration, or directly you can put the property. So we will stop here. In case you find any difficulty, we will repeat some concept again in the next lecture. So thank you.
Thank you, sir.
Thank you, sir.